Welcome back to the deep dive. Today, we are tackling something that honestly feels a bit like science fiction,
Oh, definitely.
but it is very much becoming science fact for you and me.
Yeah.
We are looking at a fundamental shift in how we process information.
A massive shift.
And I don't just mean, a faster processor for your laptop. I mean a completely different way of thinking about logic itself.
Exactly. We are moving from the predictable, comfortable world of on and off switches into a realm that is, honestly, it's a bit spooky.
Spooky is the right word.
We are talking about the transition from binary determinism to quantum probability.
Right. And we have a really interesting source stack today to help us wrap our heads around this.
Yeah.
It's a comparative analysis presentation, simply titled Bits and Qubits.
Prepared originally for senior tech leadership.
Yeah, exactly. So the mission here for this deep dive is to decode the difference between the bit and the qubit. And from what I have read in these documents, this isn't just a hardware upgrade.
No, not at all.
It feels like we are rewriting the rulebook.
It is not a hardware upgrade. It is not like going from a V6 engine to a V8. It is closer to going from a horse and buggy to teleportation.
Wow.
It requires us to completely rewire how we understand reality. We are going to look at why the bit is the concrete block of our current world and why the qubit is this fluid, mysterious sphere.
The sphere that allows for, what was the phrase? Massive solution space exploration.
Yes.
Okay, so let us unpack this. I was looking through the visuals in the source material earlier, and the first thing that hit me wasn't the text, it was the pictures.
The visual contrast is stark.
Right off the bat. On one side, representing the bit, you have this mechanical counter. It looks heavy.
Metallic.
Industrial, yeah. Has gears. It looks like something you would find bolted down in a 19th century factory.
Right, and that visual is very intentional. That mechanical counter represents stability.
No.
It is rigid. It is built for determinism. When you look at it, you know exactly what number is showing.
There is no ambiguity.
None. It is a machine that follows orders perfectly.
And then on the other side, representing the qubit, it is a totally different vibe. It is this glowing, purple, fluid sphere with an arrow floating inside it.
The sphere.
It looks organic, almost like a bubble or a drop of water suspended in space. It just looks completely unpredictable.
That is the sphere, yes. If the bit is a switch, the qubit is a sphere. It is built for complexity.
Okay.
It is probabilistic, and crucially, it is fragile. That image captures the essence of the qubit perfectly. It is something that exists in a constant state of flux.
So we have the switch versus the sphere, but before we get too deep into the sci-fi aspect of this, the source material makes a really key insight early on that I think we need to clear up for everyone.
The replacement myth.
Yes, exactly. Because I think people hear quantum computers and they automatically think, great, my next smartphone is going to have a battery that lasts forever and calculates everything instantly.
Oh, absolutely. That is the #1 misconception out there.
But the analysis explicitly says quantum computers will not replace classical systems.
They absolutely will not. You aren't going to have a quantum processor in your pocket checking your email or streaming video for you.
Right.
The source is very clear on this. Qubits are designed to work alongside bits to solve specific problems that are mathematically impossible for classical computers.
So they're just different tools.
Exactly. Different tools for different worlds. You wouldn't use a particle accelerator to slice bread.
Fair point. So let us talk about these two different worlds. We need to define the state of these units.
Okay, let's do it.
Everyone knows the bit. It stands for binary digit. It exists in exactly one of two discrete states,
0 or 1.
up or down, on or off. It is the literal foundation of modern civilization because it is unambiguous.
Precisely. It is the light switch on your wall. It is either on or it is off. If it is stuck somewhere in the middle, your switch is broken.
Right?
That absolute certainty is why our global banking systems work. It is why airplanes stay in the sky.
But the qubit, the quantum bit, is where my brain really starts to hurt. The text says it is a two-level system that behaves very differently. It exists in a state of superposition.
Superposition.
Now, superposition is the big buzzword. What does that actually mean in plain English?
Imagine that instead of being just 0 or just 1, it is a complex combination of both basis states simultaneously.
Simultaneous?
Yes, until it is measured. That is why the visual they used is a sphere.
Oh, because of the arrow inside.
Exactly. The arrow inside isn't just pointing straight up for 1 or straight down for 0. It can point anywhere on the surface of that entire sphere.
Okay, hold on. My brain rejects that.
Most people's brains do.
How can it be both? If I have a box and I put a cat in it, I'm sorry, I know, the classic Schrodinger's cat thing. But if I open the box, it is one or the other.
Right.
Are you saying it is physically two things at once, or just that we don't know which one it is yet?
That is the deepest philosophical question in quantum mechanics. Seriously. But for the purpose of computing, you have to treat it as physically being a mixture of both states at the exact same time.
Wow.
It is not just that we don't know the state, it is that the state itself is a fluid blend.
And what is fascinating to me is how these things physically manifest in reality. The source breaks down the physical manifestations.
Right.
A bit is something we can touch, metaphorically speaking. It is voltage.
High voltage is a 1, low voltage is a 0.
Exactly. It is engineering. We can solder it. We can look at a circuit board.
Yes, bits are macroscopic. We realize them through electrical current or magnetization on a hard drive.
But qubits?
Qubits are subatomic. To make a qubit, you have to deal with nature at its absolute smallest scale.
Like what, specifically?
We are talking about electron spin. Is the spin up or is it down?
Okay.
Or atom energy levels. Is the atom in a ground state or an excited state? Or even photon polarization?
That sounds incredibly difficult to manage. You're trying to use a single isolated electron as a computer part.
Yes.
How do you even hold on to an electron without losing it or bumping it?
It requires extreme isolation. We are talking about controlling individual particles using highly calibrated lasers or specific microwave pulses.
That is wild.
It is a completely different league of engineering. It is like trying to stack a house of playing cards in the middle of a hurricane.
Which leads us directly into the math.
Yeah.
Now, I know you listening might tense up when we say math, but the comparison in the presentation is really helpful.
It really is.
They call it the math of certainty versus the math of probability. Let's look at the classical logic first. The metaphor used is a coin lying flat on a table.
Right. You look at the coin on the table, it is heads, which we will call a 1, or it is tails, which we will call a 0.
It has a definite value at all times.
Exactly. This is pure Boolean algebra. True or false, there's absolutely no ambiguity.
But then we get to quantum math, superposition and probability amplitudes.
Yeah.
The metaphor shifts here. Now, imagine that same coin is spinning rapidly inside a glass bubble.
A perfect metaphor. While it is spinning, is it heads or tails?
Well, effectively neither, or both.
It is a linear combination of both.
But linear combination is a bit jargon-heavy. Let's try a different analogy for the listeners.
Okay, think of a classical bit as a single musical note. You sit at a piano, you play middle C. Boom.
Boom. That is your note. That is a 1.
Right. A single distinct note. A qubit in superposition is like a chord.
A chord.
You strike C, E, and G at the exact same time. It is not just one note anymore. It is a harmonic complex of multiple notes resonating together.
Oh, I like that.
It contains the potential of all those individual notes, but it exists in the air as a singular complex sound.
That helps a lot. So it is a rich state, not just a simple toggle.
Yeah.
The source actually throws an equation at us here on slide 6.
Ah, yes. The wave function.
It involves alpha and beta. It looks a bit complicated, but effectively, what are alpha and beta doing in this musical chord analogy?
Think of alpha and beta as the volume sliders on a mixing board for that specific chord. Alpha controls the volume of the 0 state, and beta controls the volume of the 1 state. They represent the probability amplitudes.
And there's a strict rule here, a constraint. The presentation says the sum of the probabilities must always equal 1, or 100%.
Right. You have a probability budget of exactly 100%.
So you can split it up however you want.
50-50, 70-30, or 99-1. But you absolutely cannot have 110%.
The system is always fully accounted for.
Yes. But here is where it gets really tricky. And this is the transition to the concept of measurement.
Yes, slide 7. This is the part that always melts my brain. In the classical world, with the bit, measurement is completely passive.
Right.
I can look at that coin on the table 1,000 times. I can check the state of a transistor infinitely. Doesn't change anything. The coin stays heads.
But in the quantum world, measurement is destructive.
Destructive.
The source calls it wave function collapse.
Destructive just sounds so counterproductive for a computer.
It is the nature of the beast. Go back to that spinning coin or that musical chord. If you want to measure it, if you want to force it to give you a single discrete answer.
You essentially slap your hand down on the spinning coin.
Yes, you slap it down and it stops.
It stops spinning.
You force it to become either a heads or a tails based on those probability volume sliders we talked about.
So if the head slider was up really high,
Yeah.
it will probably land on heads.
Probably. But the moment you look, the spinning stops. The beautiful chord vanishes, and you are left with just one flat note.
And once you do that, the superposition is just gone.
Gone forever. You have lost that complex mix of probabilities entirely. You have collapsed the wave.
So this begs the huge, obvious question. Why take the risk?
The payoff.
If reading the data destroys the complex data state, why are we doing this? It feels like building a massive library where the books instantly burn up the second you open them.
Because of the power of the exponent. This is the ultimate payoff. Let us compare the growth models.
Yeah, the analysis shows a chart comparing linear versus exponential growth on slide 8.
With bits, growth is strictly linear. If you add 1 bit to your computer, you add 1 unit of storage. It is a one-to-one relationship.
Right.
But with qubits, adding 1 single qubit doubles the state space.
It doubles it.
It is 2 to the power of n.
So 1 qubit is 2 states, 2 qubits is 4, 3 is 8. That doesn't sound that impressive at the very beginning.
It starts slow, but doubling gets out of hand very, very quickly. There is a mind-blowing stat in the notes here that I just love.
Let's hear it.
It says a register of just 300 entangled qubits could represent more states than there are atoms in the entire observable universe.
Wait, hold on. Just 300.
300.
It seems impossibly small. My laptop has literally billions of transistors in it.
Just 300 qubits. That is the terrifying power of exponential scaling.
Wow.
A classical supercomputer would need more bits than there are atoms in the universe just to write down the state that 300 qubits can hold in superposition.
That is hard to comprehend.
That is why we tolerate the extreme fragility. That is why we deal with the destructive measurement, because the computational density is completely unmatched by anything else in physics.
Okay, but how does that density actually help us solve problems faster? I get that it holds more data, but does it just read it faster?
No, and this is the real aha moment of the whole presentation. Think of a maze.
A maze. Go.
A classical computer is like a mouse running through a maze. It runs down a path, hits a dead end, runs all the way back, tries the next path.
So it checks every single possibility sequentially, one at a time.
Exactly. It might take 1 billion years to find the exit if the maze is big enough. A quantum computer in superposition doesn't run the maze like a mouse.
What does it do?
It is like flooding the maze with water. The water, the probability wave, fills every single path simultaneously. It hits all the dead ends and the exit at the exact same moment.
It explores the entire solution space at once.
Yes.
That is a wildly different way to think about calculating. It is not checking boxes. It is flowing.
Exactly.
But in tech, this immense power comes at a huge price.
Yeah.
The section on the engineering challenge makes it sound like an absolute nightmare to actually build these things.
Nightmare is a strong word, but it is accurate. We touched on it earlier, but let us really talk about robustness versus decoherence.
Bits are robust.
Very. Your laptop works perfectly at room temperature. You can walk it through a giant magnetic airport scanner. It handles environmental noise easily.
Qubits, on the other hand. The text visualizes them as a snowflake shattering.
That is a perfect image. Qubits are hypersensitive. Any interaction with the outside world causes decoherence.
Any interaction. Like what?
Heat, stray radiation from space, even a slight magnetic field from a nearby elevator moving up and down.
An elevator can ruin a quantum calculation.
It absolutely can. The interaction destroys the quantum state. The snowflake shatters.
So if someone turns on a microwave in the break room next door, the calculation just fails.
Potentially, yes. This is why actual quantum computers look like those giant golden chandeliers you have probably seen photos of online.
I have seen those, yeah. They look like art pieces.
They are actually massive cryostats. They are cooling the tiny chips at the very bottom down to near absolute zero.
Like outer space cold.
We are talking significantly colder than deep space, just to keep the thermal noise of the universe out of the processor.
And because they are so insanely fragile, we hit a massive bottleneck. Slide 10 calls it the phalanx metaphor. What does an ancient Greek army have to do with quantum computing?
It is about protection. In classical computing, the ratio is 1-to-1. One physical bit gives you one logical bit of data.
Simple.
But because qubits are so error-prone and fragile, we absolutely cannot rely on just one. We need a phalanx.
A formation.
We need to surround one logical qubit, the one actually doing the complex math, with dozens or even hundreds of physical qubits acting as an error correction array.
So they are basically bodyguards.
Exactly. They are bodyguards taking the bullets of environmental noise so that VIP qubit can survive just long enough to finish the calculation.
So when we hear about a 1,000 qubit processor being announced in the news, a huge chunk of that number is just overhead.
Yes. It is mostly just infrastructure to keep the system stable. The actual usable logical qubits are a much smaller number.
That really puts the engineering challenge in perspective. It is not just making them smaller, it is making them survive.
Precisely.
Now, let us talk about how the thinking actually happens inside the machine. The comparison here is logic gates versus unitary transformations.
Classical processing uses logic gates, AND or OR and RIT. It is strictly sequential.
You take a bit, you send it through a gate, it flips, you send it to the next one, step-by-step logic.
And quantum. The text uses the beautiful phrase, choreographing waves of probability.
Choreographing.
It is beautiful, really. Remember the water flooding the maze? The goal of a quantum algorithm isn't just to run sequential steps. It uses something called interference.
Like wave interference.
Think of ripples in a pond. You want to set up the waves so that the wrong answers, the dead ends in the maze, physically cancel each other out.
So the peak of a wave meets a trough of a wave, and they just flatten out.
Exactly like noise-canceling headphones.
Oh, that makes total sense.
But at the exact same time, you want the wave representing the correct answer to constructively amplify.
So you aren't hunting for the answer line by line.
No. You are manipulating the entire probability landscape so that the right answer loudly reveals itself when you finally measure it and collapse the wave.
That is so incredibly abstract compared to 1 + 1 = 2. But let's ground this for everyone. What do we actually use this for?
Right, the practical application.
We established that the bit is the universal standard for things like Excel and Instagram.
Wow.
But the qubit is designated as a complexity solver. What are the actual killer apps here?
Simulation is the big one.
Okay.
Richard Feynman, the famous physicist, he said that if you want to simulate nature, you had better make it quantum because nature is fundamentally quantum.
That makes sense.
If you want to simulate a caffeine molecule to see exactly how it interacts with the human brain, a classical computer struggles massively because the atomic interactions are simply too complex.
But a quantum computer can handle it.
A quantum computer mirrors the very thing it is simulating.
So drug discovery is a major play here.
Huge. It will revolutionize medicine. Also cryptography, specifically Shor's algorithm.
I've heard of that one.
It threatens to completely break our current global encryption standards by factoring huge prime numbers almost instantly.
Which is terrifying for cybersecurity.
Very much so. And finally, optimization problems, like finding the absolute perfect route for 1 million delivery trucks simultaneously, where the path of every single truck affects the traffic for every other truck.
The logistics applications are endless. Now, the analysis also maps this technology onto an adoption curve.
Yes.
Classical computing is sitting at the plateau of productivity. It is ubiquitous. It is totally invisible to us because it just works so well. Where exactly is quantum right now?
It is sitting at the innovation trigger. It is very much in the experimental phase.
So not ready for prime time.
It is in pristine research labs, not consumer products. We are still actively figuring out how to keep the snowflakes from melting, so to speak.
So looking forward to the future, what does the corporate data center of, say, 2035 look like? The source gives us a roadmap on slide 14 titled The Hybrid Model.
This is the key takeaway for tech leadership. The future isn't the qubit instead of the bit. It is the qubit orchestrated by the bit.
How does that hybrid architecture actually work in practice?
Imagine a massive supercomputer. The classical host, the standard CPU, runs the entire show.
Right.
It handles the operating system, the user interface, reading the hard drives. It does everything it is already perfectly good at.
Right. No need to reinvent the wheel.
But when it hits a problem that is computationally intractable, something that would take it 10,000 years to solve by brute force, it offloads that specific subroutine to a QPU.
A quantum processing unit.
Exactly.
Like how my computer uses a graphics card for games.
Exactly like a GPU. The QPU is a highly specialized accelerator.
I see.
The classical CPU says, hey, I have this impossibly complex optimization problem. Here are the parameters.
And a QPU takes over.
The QPU does its probability choreography, collapses the wave function to get a discrete answer, and sends that normal binary answer right back to the classical CPU to display to the human user.
That makes the technology feel so much more tangible.
Yeah.
It's not a magic box that replaces everything in the world. It is a turbocharger for the really hard stuff.
Right. We aren't replacing the concrete foundation of our digital world. We are just building a new kind of skyscraper on top of it that reaches into a totally different dimension of mathematics.
As we wrap up this deep dive, I'm really struck by how this changes my entire perspective on computing itself.
It is a paradigm shift.
We are so used to the idea of brute force. If a computer's too slow, just make the clock speed faster, just cram more transistors on the silicon.
Right.
But this is a shift from brute force to, well, what would you call it?
I would call it a shift from calculation to exploration.
Exploration.
Classical computers are distinct, rigid, and safe. They follow the rules of the maze. Quantum computers explore the probabilities of what could be true.
They flood the maze.
They tap into the fundamental fabric of reality superposition to find answers that simple linear logic alone just can't reach.
It is incredibly humbling. And while you listening won't have a QPU in your pocket anytime soon, or honestly maybe ever, this technology is going to silently revolutionize the medicines you take,
It absolutely will.
the new materials your cars are made of,
Yeah.
and the underlying security of your bank accounts.
It will be the invisible engine solving the world's unsolvable problems.
Here's a thought to leave you with, and this one has been bugging me since I read the very first slide of the intro. We spent all this time today talking about how weird and delicate and fragile qubits are compared to our reliable, sturdy bits.
Right.
But if the universe itself, at the atomic level, is fundamentally quantum,
Which it is.
if nature actually operates on probability and superposition as its baseline, then are our classical computers actually the weird ones?
Ah, that is the ultimate provocation, isn't it?
It really makes you wonder if our binary logic, this rigid 0 and 1 world we have built our entire civilization on, is just a clumsy, unnatural approximation of reality.
I think you are spot on.
And the qubit is actually just us finally learning to speak the universe's native language.
I think that is exactly right. For the first time, we are finally computing the exact same way that nature does.
Something to think about the next time you flip a simple light switch on your wall. Thanks for listening to The Deep Dive. We will see you next time.